All right, so welcome to episode 6. And in this episode, we're going to talk about power on reset. And the basic premise here is that when you have sequential devices such as latches and flip-flops in your circuit, given that those devices have two stable states, when they're powered on, they could be in either state. And the circuit may not operate correctly unless these sequential devices are forced into a known state. So that's the purpose of the power on reset signal. It is typically fed to an asynchronous reset input on these sequential devices and essentially forces them into a known state when power is applied. Okay, so if you don't want to watch any further, just use the MAX 708. It's a very nice power on reset chip. That's the one that I like. But I will, in the video, talk about different options that you have, which include building an RC circuit with a diode and 74HC14 Schmidt trigger inverter chip. You could also just use a debounced push button in order to generate a manual reset signal, and that's somewhat similar and again uses the 74HC14. And probably the best approach is to use a dedicated power on reset chip such as the MAX 708 or the TL7705A. But the important thing to understand is that when you have stateful devices like latches and flip-flops, and especially CPUs in your circuit, the circuit is not going to work correctly unless you have a good reset signal. All right, so here is our first power on reset circuit, the RC power on reset circuit, and the real advantage of this particular approach to generating power on reset is that it requires only very basic components. You need a capacitor, a resistor, a diode, and two Schmidt trigger inverters, which are going to be gates of a 74HC14 device. Okay, so here's how the circuit works. Initially, the positive side of this capacitor is going to be at a low potential with respect to ground. Essentially it'll be at the same potential as ground, meaning that the capacitor is not charged. So when the circuit is powered on, because there's a low voltage here, we'll get a high voltage here and a low voltage here, and that corresponds to asserting an active low reset signal here at the output of this inverter and an active high output here at the active high reset signal. Okay, but when power is applied, meaning that there's a positive voltage here at VCC, the positive supply rail, what happens is that current will flow through this resistor and charge up this capacitor. So essentially we will see a relatively slowly rising voltage here at this node in the circuit. The rate at which the capacitor charges, meaning the rate at which this voltage increases, is a function of the RC time constant, which is the product of this resistor value and this capacitor value. But eventually, once the capacitor charges up to a sufficient degree to meet the high input threshold, the positive, sort of true input threshold for this Schmidt trigger inverter, then the output of this inverter changes to low, meaning the positive, active high reset signal is deasserted, and similarly, a low output is going to be asserted here on the active low reset. In other words, that is the point at which these two reset signals say reset is done, and that's when the normal operation of the circuit can proceed. Okay, so that's sort of the basic idea, and we'll show that on the oscilloscope to see how the voltages change and how the reset signals are generated. So one important thing we have to think about, though, is that if this capacitor stays charged up when the power is off, that's actually really bad, because the next time we power the circuit on, we would be producing a high voltage here, meaning reset would immediately be deasserted. Essentially, there wouldn't be any power on reset signal generated. So we need to make sure that when power is off, that this capacitor gets discharged. That is the purpose of this diode here. So the idea is that when when power is turned off, meaning we no longer have a positive supply voltage being asserted here, provided here at VCC, what happens is that this positive potential that exists because of the capacitor being charged up is going to flow through this diode, and but in order to flow and discharge the capacitor, that current needs somewhere to go. Where it goes is that it is actually discharged through the load, meaning the other devices in the circuit. So in some sense, when the power rail it goes away, this capacitor is now trying to power the circuit. And of course, it only a small amount of charge exists here in this capacitor, and so it will, it won't be able to actually power the circuit, but that should be sufficient to ensure that the capacitor gets discharged. And that's indicated here, in my little schematic as the load, that essentially acts as sort of like a resistance. Current is going to flow through here. Okay, so here is my demo circuit that I built on the breadboard. And my load is just sort of simulated by this LED and this 1K resistor. So that provides a little bit of a load to allow a path to discharge the charge built up in the capacitor. Okay, so let's go ahead and see how this works by tracing the voltages on the oscilloscope. And the 2 points that we are going to be interested in and that we'll see on as traces on the scope are this node in the circuit, meaning the voltage at the positive terminal of the capacitor, and then we will also see a trace for for this signal, the active low reset. So essentially what we should see is this output is low for some amount of time after power is applied, but then eventually goes high. All right, so let's take a look. All right, so let's go ahead and look at the behavior of this RC power on reset circuit on the oscilloscope here. And we're going to be looking at two traces. The top trace is going to be the voltage on the positive terminal of the capacitor. And essentially when I've switched the power on, we should see that voltage sort of rise as the capacitor charges up. The second trace is the output of that second Schmidt-Trigger inverter, and that is generating the active low reset signal. And essentially what we should see is that voltage at that inverter output sort of stays low until the capacitor charges up to a significant degree, at which point it's going to go high, and that's the point where reset is no longer asserted, meaning that it's time for the system to come out of reset. The purpose of the reset signal is, of course, to allow the stateful devices in the circuit to initialize themselves to an appropriate initial state, so that operation of the circuit begins with all of the devices in an appropriate initial state. Okay, and I'm going to press a push button I've added to the circuit that will apply power. Okay, so here are the traces that we've captured, and you can see at this point, this is where I applied power. And of course, the voltage is slowly rising as the capacitor charges. This is the point where the oscilloscope triggered that the voltage became high enough for the oscilloscope to consider that to be meeting the trigger threshold. So what's significant here is that you can see at the point when power was applied, the active low reset output stays low, and these grid squares are 20 milliseconds. So for about 50 milliseconds, that second Schmidt-Trigger inverter stayed low, and then when the capacitor charged up enough, it went high, and at this point the system is out of reset. So basically this is the period of time at power on where that reset signal is being generated, and that's the opportunity for all of those devices in the circuit to use the reset signal to get themselves into an appropriate initial state. All right, so let's take a moment to address an important question, which is this a good way of generating power on reset? So I have two answers for you. The first answer is that, yes, this is perfectly fine. If your goal is to experiment and just build circuits and test them, this is going to be perfectly fine. I don't think you'll have any problems with it. However, the second answer is that if you were building an actual product, there is one important failure mode here that this circuit doesn't really address, which is what happens if there is a brownout condition, meaning that you get fluctuations in the positive supply rail, and for some short periods of time, it may fall below the voltage needed to ensure the correct operation of the circuit. The risk you run when you use this approach to power on reset is that if the brownout is short enough to not allow this capacitor to discharge sufficiently to actually generate new reset signals, then the circuit may malfunction because the brownout, affected the correct operation of the circuit, but was not long enough to discharge the capacitor to actually generate a new reset signal. So if you were to, engineer an actual product, you would probably want to do something more sophisticated than this circuit. But again, like I said, I think for experimenting and just, building circuits for fun, no problems at all. All right, so let's talk about another approach to generating a reset signal, this time generating a manual reset signal using a debounced push button. And manual reset is actually kind of a nice feature because it means you can just press a button and the circuit will reset itself. So this is actually kind of a nice idea. So we've sort of alluded to the need to debounce push buttons when we use them to generate digital inputs in earlier videos, but we haven't really ever talked about what exactly that means. So let's talk about that a little bit now. Mechanical switches, like this push button here, can exhibit a phenomenon called contact bounce. And essentially what happens is in the switch, as the conductor is basically pressed against the terminals of the switch, you don't necessarily get a clean and instantaneous sort of transition from an open circuit to a closed circuit. It kind of wiggles back and forth between closed and open, and essentially if you're generating a positive voltage when contact is made, it will maybe kind of wiggle and not generate a single high to low transition. And you can observe this on the scope if you built a little circuit. And so this is a problem because it means that you may essentially be providing sort of glitchy input to wherever you're feeding the signal that is being produced by the switch. So a debouncing circuit essentially tries to smooth out the voltage that is being produced by the switch being closed or opened. So here's an example of a debouncing circuit using a capacitor and a resistor. So here is where you will definitely be able to see that I am not an electrical engineer, so I will try to explain the intuition here. So here is my intuition for how this debounce circuit works. So when the power is applied, so VCC is at a positive voltage, essentially what's going to happen, and remember the button is not pressed, so this is open. What's going to happen is that this capacitor is going to charge up through this resistor, meaning we'll have a positive voltage on this plate of the capacitor and a lower voltage on the other plate of the capacitor. And essentially because this node of the circuit is tied to ground through this resistor, we're essentially going to get a low potential here on this plate of the capacitor. And so essentially this is going to be a low voltage. And so if you think about a low signal being fed into this inverter, that means we get a high signal here, meaning that the active low reset is not asserted, and a high potential here is going to produce a low potential here, meaning that we are not asserting the active high reset. So essentially, unless the switch is pressed, we're not generating the reset signal. All right, so now let's imagine that we press the switch here. And essentially when this push button switch is pressed, we're creating a path from VCC through this resistor into this node in the circuit. And in general, current always wants to flow from a higher potential to a lower potential. And given that this plate of the capacitor is at a low potential, and this VCC is at a higher potential, essentially current will want to flow through this path, through the switch, into this plate of the capacitor. And it will take a little bit of time to essentially bring this plate of the capacitor up to the same potential as VCC, meaning that we're going to get relatively a slow rise time here at this node in the circuit. And a slow rise time is good because it means it will essentially kind of dampen any sort of oscillations that are caused by contact bounce, if there is some. And the reason that we use Schmitt-Trigger inverters is that Schmitt-Trigger devices have inputs that implement a feature called hysteresis that essentially means that once we reach for example, if we're at a low voltage and then we eventually rise to the high input threshold, the corresponding low input threshold becomes sort of correspondingly lower, so that there's a tendency not to flip back to a low state at the input, even if there's maybe a little bit of noise or sort of wiggle at the point where we reach the high input threshold. And there's also hysteresis at the low input threshold. So if we have a falling voltage, even if it's sort of maybe wiggling a little bit, by the time it triggers the low threshold, the corresponding high input threshold, it sort of becomes correspondingly higher. And this means that Schmidt-Trigger inputs are effectively tolerant of slower rise times and slower fall times, which is exactly what we want, because we are intentionally trying to make sure we don't get rapidly changing voltages at this node in the circuit. Okay, so I did a little bit of experimentation with resistor values for this particular resistor. So if you have no resistor here at all, so if you have 0 ohms, direct connection to VCC, what I measured on the scope was a rise time of about 300 microseconds, which is significantly more than the period of time when I observed contact bounce, when I did some experiments to capture contact bounce. So that's probably fine. But if you want to slow down the rise time even more, you can increase the resistor value here. So I tried 2.7K and found that I got a rise time of about 4 milliseconds. So that's quite good. That's gonna I think definitely handle any contact bounce. Okay, so when you release the switch, essentially what's going to happen is that this capacitor is going to charge up again, and essentially a low voltage is going to be created here. Essentially, the higher potential that accumulated on this plate of the resistor is going to kind of bleed through this through this resistor, and eventually we'll get a low potential here at this node, and that fall time was relatively slow, on the order of milliseconds. So again, that's going to be perfectly fine to compensate for any contact bounce. All right, so here is a very nice power on reset solution, which is the MAX 708 power on reset IC. You can also use the MAX 707. It's more or less exactly the same. They differ slightly in the brownout voltage threshold. And the nice thing about these dedicated power on reset chips is that they essentially do everything for you. So when the positive supply rail appears, a reset pulse of a certain duration, specifically 200 milliseconds, is going to be generated on the both the active low reset output and the active high reset output, and then after that period of time, the signals are deasserted, and then the circuit begins its normal operation. And another really nice feature of these chips is that they have a manual reset input, which you can simply wire to a push button, such that if the push button pulls that input low, a reset pulse will be generated. And this is a very simple way you can add a manual reset to your circuit, which is quite useful for debugging. Okay, so let's look at the operation of this circuit on the oscilloscope, and we're going to probe both the positive power rail here on channel 1 and also the active low reset output on channel 2. And essentially when the power rail goes high, 200 milliseconds later, we should see this active low reset go high. So in other words, for 200 milliseconds, the active low reset will remain low, essentially forcing the circuit into reset. Okay, so let's take a look at that on the scope. All right, so here we have the oscilloscope set up to capture these signals. Signal 1 is going to be the positive supply voltage. Signal 2 will be the active low reset output, and I've got it in single shot mode, and we're going to trigger on a positive edge on channel 1, which is the positive power rail. Okay, so I'm going to power on the circuit. Okay, and what you see is here is the point, obviously, where the power rail appeared, so it goes from 0 to 5 volts and is at a steady 5 volts. And then this is the output of the active low reset signal, and each of these grid squares is 50 milliseconds, so exactly 50, 100, 150, 200 milliseconds later, the active low reset goes from low, asserted, to high, not asserted. And so at this point, our circuit is now out of reset. So works exactly like the data sheet says that it does. All right, so here is one last power on reset circuit, this time using the TL7705A power on reset chip. And I built and tested this circuit not so much because I'm a big fan of this chip, but more because I noticed that it is, fairly widely available and widely used for this type of application, and I thought I'd give it a try to see how it works. One disadvantage of this chip compared to the Mac 708 is that it does require some external components, and in particular, there are 3 resistors and 2 capacitors. This particular capacitor connected to pin 3 does choose the time constant that determines the length of the power on reset pulse, and so it's potentially useful to have a little flexibility in determining that duration. Okay, so as before, we will test the circuit on the breadboard and look at the traces on the scope, and once again, channel 1 is going to monitor the positive supply rail, and channel 2 is going to monitor the active low reset output of the chip. Okay, so let's look at this on the scope. All right, so here we are looking at the oscilloscope trace for the TL7705 power on reset chip. Once again, the first channel is going to capture the positive supply voltage rail. The second channel will capture the output of the active low reset output on the chip. And I've got it set up to single shot on a rising edge on channel 1, which is the positive voltage rail. All right, so I'm going to power on the circuit. All right, and so here are our captured traces, and here's the positive supply rail going high. And what you can see is that the active low reset output does indeed stay low for some period of time. In this case, the grid squares are 5 milliseconds, so it looks like we're getting a pulse of about 15 milliseconds. That's choosing a 1 microfarad capacitor to essentially set the timing constant that determines the length of this reset pulse. And then after 15 milliseconds or so, the reset is deasserted, it goes high, and at that point our system is out of reset. So once again, looks perfectly reasonable. All right, that's it for this video. Please do see the video description, and there's a link to the series website, and you will find there schematics for each of the circuits presented here, and also a little bit of information on how you can actually buy the Mac 708 and TL7705A chips, which are really useful, and I would definitely recommend you using one of these for generating reset for your circuit. All right, so in the next video, I am actually going to start doing stuff with the 6809 CPU, so I will see you then.